Welcome back, everyone. Grab your notes, grab your coffee, and let's get right to it. Today's explainer is your ultimate high-yield final exam review session for coastal morphodynamics. If you want to guarantee that you ace this section of your geography exam, you are exactly where you need to be. We're going to lock down the mechanics of how our coastlines are constantly being shaped, torn apart, and rebuilt.
Here's the syllabus for today's session. We're hitting 4 main areas: geography exam prep on coastal waves, constructive versus destructive waves, the mechanics of wave refraction, and shaping coasts through erosion and deposition. Mastering these 4 areas is the absolute key to understanding our coastlines.
Section 1. Geography exam prep on coastal waves. Okay, let's dive right into this and lay down the absolute baseline knowledge you need.
I need you to commit this exact definition to memory. Seriously, highlight this. Waves are forward-moving surges of energy formed by friction between the wind and the sea surface. You know, when you look out at the ocean, it's so easy to just think, oh, I'm watching water move. But actually, scratch that, you're watching energy move. And it's the friction from the wind blowing across the sea surface that transfers energy into the water. Never forget that. Waves are energy moving through water, triggered by the wind.
Now, depending on how much of that wind energy actually gets transferred and what happens when that energy finally smacks into the shoreline, we classify waves into 2 main camps: constructive and destructive. This dichotomy, it's basically the foundation of everything else we're going to cover today.
Section 2. Constructive versus destructive waves. Let's move right into it, because this right here is the most heavily tested material, the classic face-off between the builders and the destroyers. Look, if you only remember one single thing for the test, please make it this. It all boils down to the mechanical difference between swash, that's the water moving up the beach, and backwash, the water dragging back down into the sea. For constructive waves, the swash is the powerhouse. It actively pushes material up onto the shore. But for destructive waves, the backwash is way more powerful than the swash, aggressively ripping material away. Consider this your ultimate cheat sheet data for the exam. Let's look at the numbers. Constructive waves, they're the low and slow builders. They've got long wavelengths of up to 100 meters, low heights of less than a meter, and a super chill frequency of just 6 to 8 waves per minute. Now contrast that with destructive waves. These are rapid fire and aggressive. They have short wavelengths under 20 meters, heights greater than a meter, and they crash onto the shore with a high frequency of 10 to 12 waves per minute. So what's the actual geographical outcome of those low, slow builders? Well, because they're low-energy waves with a dominant swash there, they are the true engines of coastal deposition. They gently drop off sand and pebbles, gradually building up wide, beautiful beaches. And get this, constructive waves can actually build up a beach by several meters over a single calm summer. You're mainly going to find these guys doing their work on lowland coasts that have really shallow, gentle gradients. Contrast that immediately with the destroyers. Destructive waves are incredibly high energy, usually whipped up by fierce local winds and massive storms. Because that backwash is so dominant, their main gig is coastal erosion. They violently rip sediment away from the beach, drag it out to sea, and literally scour and erode solid cliff faces. You'll see these absolute monsters operating on steep beach gradients where their energy just slams directly into the coast. Section 3. The mechanics of wave refraction. Let's see how this builds into the essay question that absolutely separates the A students from the B students. Let's carefully unpack this definition. Wave refraction is the process where a wave front actually changes its physical shape and loses speed. The primary trigger here, depth. Specifically, coming into contact with the shallow seabed. The friction with the bottom literally steals the wave's speed and forces it to distort. Now, what's really interesting about this is the exact physical chronology of the bending process. Visualize this with me. Step 1. The long, straight wave approaches the shore and hits shallower water. Step 2. The part of the wave that hits the shallow water first slows down, right? But the part still in deeper water just keeps barreling ahead. This difference in speed causes the entire wave front to physically bend around the coastal features. And step 3, because of that bending, the wave's energy doesn't hit the shore evenly. It gets either highly concentrated or widely dispersed. But here's a crucial side effect you literally cannot forget on exam day. What happens if the wave doesn't bend completely? Well, if refraction isn't completed and those waves don't become perfectly parallel to the shore before they break, they hit the beach at an angle. That angled approach is the absolute engine behind longshore drift, which is the process that continuously moves sediment steadily down the length of the coastline. To put that into perspective, longshore drift can move hundreds of thousands of cubic meters of sand along a single stretch of coast in just 1 year. It's wild. Section 4. Shaping coasts through erosion and deposition. This brings us right into the final phase of our explainer, looking at the massive geographic consequences of the mechanics we just talked about.
Think about a jagged, irregular coast. The jetting headlands force the incoming waves to bend around them, concentrating all that violent wave energy directly onto their flanks. It leads to intense, destructive, and erosive activity. But the bays? They're sheltered. As the wave expands into a bay, its energy is widely dispersed, drastically reducing its power. This low-energy environment encourages deposition, allowing those constructive waves to build up beautiful bayhead beaches.
So, tying it all together, we get a relentless coastal cycle. It's basically a permanent geological drama of destruction and creation. Headlands face continuous pounding erosion. The bays continuously collect sediment through ongoing deposition. And all the while, longshore drift is acting like a giant conveyor belt, continuously moving that eroded sediment right along the coastline.
Which leaves us with this final, provocative thought to ponder right before your exam. If the jutting headlands are constantly being eroded back, and the recessed bays are continuously being filled in with new sediment, what is the ultimate long-term fate of a highly irregular coastline? Just think about the geometry of that over thousands of years. All right, great job reviewing today, everyone. Study this material, trust your preparation, and go ace that exam.